Good morning, everyone. I am Dr. Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. I welcome you all in this lecture of aircraft stability and control. I am in the module 5th, which is dynamic stability, and in this I am going to discuss about the definitions and the terminology. So in this dynamic stability, I am going to discuss about some of the important dynamic stability terms and the terminology. First one is roll mode. So the roll mode has a real root and a first order non-acceleratory response that involves almost a pure rolling motion and the x about the x stability axis. It is usually stable at low and moderate angle of attack, but may be unstable at high angle of attack. The roll mode can be excited by a disturbance or an aileron input. So what is the roll? Okay, so just you can see here, the aircraft which is here, I want to make roll. So if I want to make the roll, it means this is the longitudinal axis, or it is also called the x-axis, which is the body axis passing from nose to tail via the center of gravity. So this is the x-axis from here to here, and if my wings are going like this, up or down, then it is a rolling, and this rolling can happen by the two means. One is by the pilot itself. Pilot will try to move this aileron. If you see one aileron, another aileron. So if pilot want that right wing should go up, so he want that the lift of this wing should be more. To have the lift more, this aileron has to go down. So if this aileron is going down, here lift will be more, and this side, this aileron will go up. So here lift will be less. So the left wing will go down and right wing will go up. So here roll will take place. This roll, if for a low angle of attack and for moderate angle of attack, it is stable. But as and when the angle of attack of the aircraft, it means this angle and then rolling. So within a limit, maybe 8 degree or 9 degree, it is okay. But as and when you cross the 10 degree angle of attack and give the rolling also, aircraft may be disturbed to unstable. So that we have to take care that during the rolling, our angle of attack should not go to a beyond limit. Next point is damping ratio. So the damping ratio provides an indication of the system damping and will fall between -1 and +1. For stable system, the damping ratio will be positive and it will be between 0 and 1. So this zeta, this is called the damping ratio, and this value of this thing goes from -1 to +1. But for the stable case, 0 to +1 for stable. Okay, for unstable, -1 to 0. This is unstable. And for the neutral, zeta is equal to 0. So these are the values. So by the finding the damping ratio of any dynamically operated system, we can assess that whether this aircraft is dynamically stable, dynamically unstable, or it is a dynamically neutral stable. If the value of damping ratio is 0 to +1, we can say that the aircraft is dynamically stable. If the zeta value or the damping ratio value is -1 to 0, in between, we can say that the aircraft is unstable. And if the damping ratio is 0, then it is neutrally stable. It will remain in the same position without disturbing anything. So this is the damping ratio. Next is damped frequency. So the damped frequency represents the frequency that the system actually oscillate at with damping present. So in this, if you see, if any system, if you see this spring mass systems like this is the mass, and so this is the here mass, this is here spring, and if something is here, then it is a damping here, damping. This is the mass and this is the spring. So in this, what happens? If these dampers are not there, it will start oscillating like this, like this, like this, like this. It will stop. But if dampers are there, slowly it will come down to original position. Okay, that is the specialty of this damping frequency. Natural frequency. The natural frequency is called when there is no damping at all, a zero damping. So the natural frequency is the frequency that the system would oscillate at if there were no damping. It represents the highest frequency that the system is capable of, but it is not the frequency that the system actually oscillates at if damping is present. So the natural frequency, we have to understand that the how much maximum this system can oscillate without damping, and how much it is capable to oscillate as per the required system. We have to understand this natural frequency very well, so that this application can be natural frequency can be applied to understand the dynamic behavior of the aircraft. Next is Fugard mode. The Fugard mode is characterized by complex conjugate root with a relatively low damping and natural / damped frequency. It is long period. Fugard is long period. It is demonstrated by trimming the aircraft in level flight, then putting aft stick for approximately 2 to 3 seconds, bleeding off some air, and then returning the stick to the neutral or trimmed position. The resulting response is usually oscillatory with sufficient vibration in pitch, attitude, and airspeed. Then the angle of attack remains relatively constant. Okay, so in this, the angle of attack is remain constant, and aircraft moves in a long period. It means it is going like this, going like this, going like this. This period is very long, and the velocity, kinetic energy will convert to potential energy. So here it is a 0, and this going to potential energy, again it is kinetic energy, again potential energy. So all this energy transformation take place. Velocity will vary, but angle of attack will be constant. Okay, so these things we have to understand that this is the Fugate mode. Now, Harper rating. Harper is a decision tree for pilot to rate a specific mission task. The pilot begins decision process at the lower left corner. The Harper handling qualities rating scales, that is called HQRS. Sometimes Harper rating scales is a pilot rating scale, a set of criteria used by test pilot and flight test engineer to evaluate the handling quality of aircraft while performing a task during the flight test. So this Harper is a scale. During flight test, during maintenance test of the aircraft, the pilot as well as the flight engineers, they will evaluate that what is the level of Harper handling quality of the aircraft. How much smooth, how much difficult, how much it is behaving properly or not. This rating is given by the Harper rating. The responsibility of this Harper rating stands with the pilot of the aircraft as well as for flight engineer of the aircraft, and these people will decide this Harper rating, and it indicates the quality of aircraft during flying. How smooth, how difficult, how it is sluggish, the control and all the parameters are understood by understanding the Harper rating. Here something is given here. It is Harper handling quality rating. If you see here, adequacy for selected task or required operations, then aircraft characteristics, demand on the pilot in selected task or required operations. In this you can see excellent, highly desirable, good, fair. These three categories are there. Then here pilot compensation not a factor for desired. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and the last is 10. So it is in improvement mandatory in this. Is it controllable? If it is like this, then you will get, aircraft will get 10 points. 10 means not good. This if Harper 1 is the best and 10 is the worst. So it is taken from NASA. I have taken this slide. So here you can see deficiencies required improvement, deficiency to warrant improvement. If these all things are over, it will go yes. And this 3, 1, 2, 3, if your aircraft is there, this aircraft is very smooth. If you are getting everything is good, then it is excellent. If 1 or 2 things are missing, it is a good. If 2 or 3 is not, then it is a fair. But after that, this and this is not at all acceptable. However, this can be improved and it can be reached in this Harper handling qualities. So like this, we can understand and we can decide the Harper handling qualities. Next is spiral mode. So this you can see here in this picture also. So first I will discuss about spiral mode. So the spiral mode is first order response. It is a real route that involves a relatively slow roll and yawing. So in this roll and yawing, okay. So in this roll plus yawing motion of the aircraft, it may be stable or unstable. The spiral is usually initiated by a displacement in roll angle and appears as a descending turn with increasing roll angle if unstable. If the spiral is stable, the aircraft simply returns to wing level after a roll angle displacement. So here you can see that we have to roll the aircraft. Okay, so roll and yaw. So it is rolling and yawing. Rolling, it is rolling and yawing. But it will start like this, and it will fall if it is uncontrolled. If it is unstable, there may be an accident, and it is, you can see here that here is a graveyard spin. This is a graveyard spin. If your spin is starting from this point, if you have taken a very serious roll and yaw, it will start like this, and again the second round, if you are not able to control, it will start and it will ditch here. It is a crash. So it is called the graveyard spin. If you make a very huge turn and roll, a high angle of roll and high angle of yaw, then there is likely to happen, and if pilot is able to control here, and in this only it has to come here, and again it has to land like this. But if you see here, another case, here you have come and you are rolling here, a very smooth rolling, and this smooth rolling you have come here, again here you are not able to control, again it will go for a graveyard, and here again crash will be there. So your rolling and yawing angle, it should be within the limit, and pilot has to take the action in a first itself, in this only. If pilot is not able to control here and it has reached here, then it will be crashed. So the spiral mode is a very dangerous activity, and pilot has to try to avoid such type of maneuver normally to save the aircraft. Next is steady state solution. A forcing function is included with a non-homogeneous differential equation, and the solution is called the non-homogeneous or particular solution. It is also called the steady state solution when we are dealing with aircraft response. So time constant, the lag time associated with this rise to the steady state value is an important consideration in determining the acceptability of the response from an aircraft handling qualities standpoint. This lag time is typically quantified by the time constant tau. Okay, so this time constant is a very important parameter for determining the acceptability of the response. How much time it is taking to give the response and come to its equilibrium or the required condition. Characteristic equations. These equations are used for understanding the dynamic stability of the aircraft. So the characteristic equation of a transfer function is obtained by setting the polynomial in the denominator of the transfer function equal to 0. The characteristic equation determines the dynamic stability characteristics of the response. So by finding these characteristic equations, we can find out whether the aircraft is dynamically stable, unstable, or neutrally stable. Transfer function. A transfer function is defined as the ratio of Laplace transforms of output to input. It is expressed in Laplace notation. Short period mode. So it is opposite to the phugoid. Phugoid is long period, and here is the short period. Within a very less time, the response is taking place. So the short period mode is characterized by complex conjugate root with a moderate to relatively high damping ratio and relatively high natural frequency and damped frequency. Okay, so in this frequency will be high, damping frequency will be high. It is easily demonstrated by first trimming the aircraft and then disturbing it from trim with a forward aft neutral pitch stick input, commonly called a doublet. The resulting response back to trim may be either first order exponential decay or the second order oscillatory decay. So this short period mode is also very important to understand the dynamic stability of the aircraft. Next, another mode is Dutch roll. So Dutch roll is a neutral aerodynamic phenomena in swept wing aircraft. It is caused by the design having slightly weaker directional stability than lateral stability. The result is the tail of the airplane seeming to wag or move left and right with slightly up and down. Okay, so Dutch roll, this you can see the top view here. 1, 2, 3, and in this you can see that the tail will go. You can see it is here, this tail is right, here is left, again right. So like this it is happening here, in this way, and your aircraft is moving like this, again like this, again like this, again like this, again like this. In this way your aircraft will start falling down, and if you see from the top, the tail will go right, left, right, left, right, left. In this way the Dutch roll is happening. So here I have shown this is the front view. This, if you see from the front, if you see from the top or the bottom, you will see that aircraft is moving in this direction. So this type of motion is called the Dutch roll. And now I am references: Robert C. Nelson, Aircraft Stability and Automatic Control, NPTEL lectures of Aircraft Stability and Control by Professor A.K. Ghosh, IIT Kanpur. This is the link for the lecture. Thank you very much for listening the lecture. I have completed my Aircraft Stability and Control course for today, and thank you very much for being with me. If any query, you can send the mail to me in this. This is my mail. This is my mail. You can, any query I can address in this mail. Thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.